All right, we're going to do a multiple mass example. So thinking back to how we did multiple masses before, we always had a common force and we always had a common acceleration. The only difference now is instead of only having some of the forces equals ma, we're also going to have some of the torques equals I alpha. So if it's rotating, we're going to use the torques. If it's moving, we're going to use the forces. If it's doing both, we got to use both. Okay. And one extra little bit is because we have a common acceleration, but we also have this angular acceleration, we need to link those two together. And so how we link those two together is we can say that the tangential acceleration of the string and the object connected to that string in this case is equal to alpha times the radius, and this is the connecting radius. So this is basically where that string is attached, okay? So this is kind of our setup. We need to generate equations based on what it's doing, link them together with a common third law pair force, like a tension, and a common acceleration using this link as well. So let's go ahead and give this a try here. Now this method is really good at finding accelerations and forces. In this case, I believe they ask us to find a velocity. So let's go ahead and read this question quick. A disk with a light string wrapped around it is allowed to rotate about a frictionless axis. A block is attached to the other end of the string and released from a height h. Find the acceleration of m2. Oh, we are finding acceleration, so we're good. All right, so we'll leave that out. They give us the mass. M1 is 8 kilograms. The radius is 0.42. M2 has a radius of 1.2, or a mass of 1.2 kilograms. All right, so let's set this up. So M1, that's our top one here. It's not moving, it's just rotating. So I'm not going to have a sum of the forces equation for it. I'm only going to have a sum of the torque equation for it. So I have the sum of the torques is equal to I alpha. M2, it's not rotating, it's just moving linearly, so I'm only going to have a sum of the forces equation for this one. All right. Now here is the acceleration I'm trying to find, and I will note that this angular acceleration is related to the acceleration of that block. Okay, so as in our multiple mass problems before, we need to identify the direction of acceleration for each. So we're going to go ahead and identify that this is going to angularly accelerate this way, this is going to linearly accelerate this way, and make those both positive. That's our idea behind that common acceleration. They're both going to need to be positive here. All right, so let's generate our equations. So this is the positive torque direction. So I see that I have tension acting on it. This one down here also has tension and M2G. Now this disk also has an M1G and some supporting force, Fy I'll call it, but because that's at the axis of rotation, Mg and Fy are not going to produce any torques. Only the tension is going to produce torques. It's producing it in the positive direction as I've defined it here. And so I have tension times radius 1 is equal to I. Now they said it was a disk, so I can look at the table and see that I have a 1/2 M1 R1 squared I value times alpha. Now this is where we're going to always, and I hesitate to say it, but always we're going to substitute in for alpha. And I'm going to show you the reason why in a second here. So I'm going to go ahead and solve for alpha. So alpha is going to be the linear acceleration divided by the radius. And so I'm going to go ahead and put in that linear acceleration divided by the connecting radius. So the string is attached to the radius R1. Now the reason I said we're always going to do this is because I see one of my R1s cancels, and I see the other R1 cancels. And so all of those R's fall out of that equation for me, and so I'm just left with tension is equal to 1/2 M1A. This is my common force. So I'm going to go ahead and be able to substitute that into my other equation. So let's go ahead and build that. So the sum of the forces are going to cause M2 to accelerate. Down is my positive direction. So I have M2G minus tension equals M2A. We are trying to solve for A, but I have two unknowns, tension and acceleration. So what I'm going to do is substitute in. So I have M2G minus 1/2 M1A equals M2A. Go ahead and Move this 1/2 M1A over, factor out an A, so I have M2G equals M2 plus 1/2 M1. We factored out that A. And so now it's up to us to divide it over and plug in our numbers. So M2 was 1.2 times 9.8, all divided by M2 again. So 1.2 plus 1/2 of the original, which was 8 for the disk. And that will give me an acceleration value of 2.26 meters per second squared. If they ask us to find the tension in that string, we could just plug that acceleration back in over here and find that tension. So again, just to recap all that, we are going to be generating equations based on if it's rotating or if it's moving linearly. We are going to be connecting those equations with a common force. So we're looking for that third law pair again. We're also going to be connecting them with common accelerations. So we're going to have to make sure that we identify both accelerations as positive so that we can link those together with a connecting radius. All right.